Okay, as always, we have questions waiting for us on the Socrative app. These are all review questions here today. Let's see how we did with them. And the first 5 here, actually, I'm trying to think. I think all of these are ones that you should be able to rattle off just like this. So you should be able to knock these off in a minute or two. So let's look at the first one here. It says, assuming a constant number of moles and a constant temperature, if the pressure of a gas is doubled, then the volume will be halved. Come on, folks. Okay, because the relationship between pressure and volume is inverse. It is an inverse relationship. As one increases, the other will decrease. Okay, assuming a constant number of moles and a constant pressure, if the temperature of a gas is doubled, then the volume will double as well, because these two variables are directly proportional. Good. Next one. Assuming a constant number of moles and a constant volume, if the temperature of a gas is doubled, then the pressure will double as well. And that's because pressure and temperature are directly proportional. Assuming constant pressure and constant temperature, if the number of moles of a gas is doubled, then the volume will double as well, because the number of moles and the volume are directly proportional. Is this right? Yeah. Okay, we got it. Assuming that the pressure, temperature, and volume remain constant. If the molar mass of a gas is doubled, then the density will double as well. That's how we started this particular unit. We had the demo on the gases, so that's a direct proportion. This is one that you did in lab. Now, when you did lab, I don't think you took partial pressures into consideration, and we didn't really have a chance to explain this at the end of the hour on Tuesday, but hydrogen gas is collected over water using the following reaction. The partial pressure of the hydrogen gas collected is blank to atmospheric pressure, and it is less than atmospheric pressure. And why is it less than atmospheric pressure? What's that? No, it's not the fact that it's a lighter gas. It has nothing to do with it. Okay? But good guess.
Molar mass.
What's that?
Small molar mass.
No, it's kind of the same idea. That's not it. Okay, when you collect the hydrogen over water like you did in a lab, it's not only hydrogen that comes through there. I know there's a little bit of air in your test tube, and we're not counting that, but what else gets collected when you bubble through water? What are you saying? No, not oxygen. Water vapor. Water vapor is going to come through. Whenever you bubble anything through water, it's going to contain water vapor. So if we were to look at this, let's see what I have. Here we go. If we were to look at the total pressure, this is kind of how we looked at Dalton's law of partial pressures the other day. We say that the total pressure is equal to the sum of the partial pressures that comprise that mixture of gases. So in other words, if we were to talk about that total pressure, the total pressure would be equal to the pressure of hydrogen that you're collecting plus the partial pressure of any water vapor that's contained in there. And we refer to that water vapor pressure as being the vapor pressure right here. And that'll depend upon the temperature. So when you did that lab, and I do the same thing when I teach the lab as Professor Lutz would have done, but when you do that lab, if you want the real, true, correct results of there, you look at whatever that temperature was at the time. And so ordinary room temperature is somewhere around 20 to 25 degrees Celsius. This table here then shows what the vapor pressure is of water at those various temperatures. And so let's say we were at about 22 degrees Celsius, which is probably about the condition, well, the labs are probably really warm there for a while, aren't they? Yeah, so maybe you were close to 25, let's say it's 25 degrees Celsius. So if the atmospheric pressure when you did that lab was, say, let's say it would have been 740 millimeters of mercury, and at 25 degrees Celsius, we would say that the water vapor pressure would have been equal to 24 millimeters of mercury. Then the pressure, the partial pressure of the hydrogen gas you collected would have been how much? Or how would you find that? It's going to be a very simple calculation. What's probably one of the simplest mathematical calculations we could do? Subtract, exactly. So we would then subtract the two and we'd say that the partial pressure of hydrogen that you collected would be 716 millimeters mercury, which again is less than the atmospheric pressure, and is due to the vapor pressure of water through which you collect it. And so ordinarily you didn't do, I don't think you did that in your lab, did you? You didn't take into account the water vapor pressure? Okay, and you did a few approximations in that lab itself, but we wanted to be really precise in that lab, what we would have by rights done is we would have subtracted out the vapor pressure due to water, because you would have been collecting that hydrogen gas by bubbling it through water. When you bubble it through water, it is going to collect that water vapor. Now, this is a table of vapor pressures at various temperatures. We had one more question on here, and in your Socrative app it says the boiling point of water is, and again, as we mentioned, it depends upon what the atmospheric pressure is. So if we come back to this table here that we looked at the other day, we define the boiling point as being the temperature at which the vapor pressure of the liquid is equal to the atmospheric pressure. And in this case here, we said that the reason why we know 100 degrees Celsius as being the boiling point that we ordinarily talk about is because the average atmospheric pressure at sea level is 1 atmosphere, or 760 millimeters of mercury. And that's why we identify this temperature as being the boiling point. But if you were to go somewhere like Denver, the mile-high city, you're at a high altitude, there's less atmosphere above you. In Denver, the boiling point of water is actually going to be closer to 95 degrees Celsius, because at a higher altitude, your atmospheric pressure is going to be lower. Okay, so it's a very simple thing like that. And if for whatever reason you went to a place like Death Valley, which sits below sea level, ordinarily a place like that is going to have atmospheric pressures on the average that are greater than 1 atmosphere, then we'd expect to find boiling points that are a little bit higher. But it's one of the reasons, if any of you do any cooking, I don't know if anybody does that anymore, but if you do, you might look at a cake mix, for example, and one of the things you're going to find on a package of cake mix is high altitude instructions. And those high altitude instructions come from the fact that at higher elevations, on average, your atmospheric pressure is less. As a result, then your water is going to wind up boiling at a lower temperature. And because it boils at a lower temperature, if you're heating stuff up, like baking in an oven or whatever, if you're talking about the water beginning to boil, it's going to be doing so at a lower temperature than at 1 atmosphere. So any questions on those Socrative app questions? Yes?
Do we have to memorize this table?
Oh, by all means. Every single value in here you got to memorize.
Okay.
You want to do that?
No.
Okay. I don't want you to do that either. So just go ahead and you'll have this table provided for you if you need it on an exam. Now, one other thing that this is used for is something called relative humidity. If you've, now see, I'm a big geek in lots of things, but I'm a big weather geek. If I wasn't going to become a teacher, I was going to become a meteorologist, and so I would pay attention to stuff like the weather, and we talk about the relative humidity. And when we talk about the relative humidity, basically what the relative humidity is a measure of the amount of moisture that's in the air compared to the amount of moisture that the air could hold at that temperature. And relative humidity is always given in values of percentages. Okay? So you might say that the relative humidity is 95%, or the relative humidity is 25%. And if you see a relative humidity of 25%, that means that the air is holding 25% of the moisture it could hold at that temperature. So the way that any percentage works is, of course, we always take the part and divide it by the whole and then multiply by 100. And so when we do the relative humidity, we talk about the amount of moisture the air could hold. So let's say, I'm trying to think if today would be a good example. Let's talk about the middle of today. The middle of today, say in the afternoon, the temperature will probably reach 10 degrees Celsius. Let's just make that up. Let's say that the high temperature today is going to be 10 degrees Celsius. And 10 degrees Celsius would be a good approximation. That's about 50 degrees Fahrenheit. Okay? So let's say that the high temperature today is going to be 10 degrees Celsius. At 10 degrees Celsius, we could say that the air could hold up to 9.21 millimeters of mercury of water vapor. Okay, that's what the vapor pressure could be. If the amount of water vapor was that much in the air at that point, we would wind up seeing condensation either in the form of fog or dew, something where that moisture would be coming out of the air. Okay, and we give a term to that value. We call that the dew point. So again, if you pay attention to the weather and you hear about the dew point is a temperature at which, if the temperature were to immediately drop to that temperature, any moisture that's in the air would condense out either in the form of fog or as dew. And that's why we call it the dew point. So let's say today, and the dew point temperature is always the same as the actual temperature or less than. If the dew point is identical to the air temperature, then we would have a condition of 100% relative humidity, because the air would be totally saturated with water vapor. But let's say that the temperature, let's say that the actual temperature was, the actual temp was 10 degrees Celsius, and let's say that the dew point was 5 degrees Celsius. Okay, let's say that these are the conditions at noon today. Okay, if these are the conditions at noon, what this would mean, again, is that the air could hold up to this amount of water vapor. But if the dew point was 5 degrees Celsius, that means if the air immediately cooled from 10 degrees Celsius down to 5 degrees Celsius, then that water vapor would wind up condensing out as either dew or fog. So if you want to calculate the relative humidity with these conditions, you would take the part, which in this case the part is the actual amount of water vapor in the air, which is going to be the 6.54 millimeters of mercury. Again, this would come from the dew point. Then we'd divide it by the vapor pressure by the actual air temperature at this point, which is the amount that it could hold, which would be 9.21 millimeters of mercury. And then we take this result, multiply it by 100, and this would wind up giving us the relative humidity. If you run it through your calculators, you can do that quickly. Eyeballing it, that appears to be somewhere around, what, 70%? If you do that, anybody have that?
71%.
71%. So we would then say under these conditions, this would be a 71% relative humidity. And so that's where that result comes from. So next time you pay attention, so again, this is saying that the air is holding 71% of the moisture it could hold at that temperature. Now the relative humidity can never be above which percentage? 100%, exactly. Because once we get up to 100% relative humidity, then any moisture or water vapor that's in there will wind up, again, condensing out as dew or fog. Any questions? All right, we had a contest in here the other day with relation to our National Mole Day. The correct answer was 3,459 pieces, which if you converted that to moles is 5.744 times 10 to the negative 21st. I wound up with some very bizarre answers. Some of you had like positive exponents here, And of course, remember that if we talk about the mole of something, like if we had a mole of ping pong balls that covers the entire Earth 60 miles deep, so if you had like more than a mole of candy pieces, you're probably filling the Earth miles deep with candy pieces. So the correct answer was this. The closest answer in all of the sections was 3,500, which is 5.812 times 10 to the negative 21st. The closest guess in this class was 4.577 times 10 to the negative 21st. That was Aaron. How about that? There you go. But you weren't the closest of all of them. Jack, you were number 2 in here. I don't remember what you came up with. You were actually quite a ways off, but there was other people that were way, 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 way further off than you were. So, all right. Everybody understand the calculation now? You get it? All right. Now, of course, we can't let Mole Day slip by without at least one more thing. You guys know what these are? Well, yeah, you're pretty close. You're pretty close. It's actually 3 moles. Yeah. And you know what these are? Well, these are molasses. All right. How about that? Now, I got to figure out how to get off of this thing here. Oh, there we go. See, ain't that good? You guys actually laughed today. That must have been funny. Huh? Wow, that's better than the other day. Okay, so from here, let's see what we have. Oh, we got a demo. Okay, the demo I'm going to do here is this one set up. And this is the one that you're going to need to move aside for just a bit, Vera, either over here or there, for just so I don't spill on you or anything. What I have here is I have a tube, and inside of this tube I am going to carry out a reaction between these 2 gases. They are ammonia gas and hydrogen chloride gas. Now, this here is an acid-base reaction, and up to now, when you've thought about acid-base reactions, you've not thought about them occurring in the gaseous phase. You've thought about them occurring in the aqueous phase. We've been thinking about them occurring in water, okay, as a medium. But turns out that we can react gases together. And to do that, what I've done here, and I'm going to set this aside so I don't knock this over, I have some concentrated hydrochloric acid over here, and I have some concentrated ammonia over here. What I'm going to do is I'm going to put on these gloves here in just a moment. I am going to open up these, well, actually let me open them up so you can see how they react. We'll loosen this one up here. We'll loosen this one up here a bit. And we'll show you what a non-aqueous reaction looks like. In other words, this is a reaction that's not occurring with water as a medium. So now if you can see this, do you see the white fog coming up here? The white fog that you see is actually super tiny particles of ammonium chloride. Now if you were to walk back into our chemical storage room, you'll see that we have stored in there our acids in one cabinet, our bases in another cabinet. And even though we have them stored, we have them sealed up in these containers, if you look on the outside, it's going to look like there's a white residue that's on the outside of them. And that white residue is a buildup of all sorts of chemicals that come together that wind up forming these solids, just like these are reacting together right here. And every now and again we have to wipe them down, because it doesn't matter how tight we seal them, tiny amounts of these gas always wind up escaping from there. So now, of course, I can't do a demo without asking you some sort of question. So what we're going to do here is we are going to ask you a question, and the question we're going to ask is this. Okay, I am going to introduce these gases into this tube on each end. I have them set up just like they are for you. I have HCl on your right, Is that correct? I need to do this correct. So, geez, I better get these set up right. So it's on your right. There we go. My left. Does that look right? I'm sorry, I'm having trouble with my... Okay, HCl is over here. There we go. So what I'm going to do is I'm going to introduce them into this tube at the same time. They're going to migrate down the tube and react. We're going to see evidence of reaction when a white ring forms on the inside of this tube. So the question is, will that ring form in the middle? Do you think it's going to form closer to the NH3 side or closer to the HCl side? I'll give you a couple minutes to think about it here, talk with a neighbor, and get your answers locked in. And again, I want you to think about this one.
He's not going to trick you this time.
And I'm just going to go ahead and do it. You don't have to lock in your answer yet. I want you to lock it in here in a bit, because this reaction will take about 5 to 10 minutes for it to migrate down. Okay, so it's going to take a bit. Here I'm dipping them in to liquids. I am putting them in the ends simultaneously, and then I am closing them up. There we go. And I've made a mess, which I need to clean up over here. So again, this one's going to take about 5 to 10 minutes. We'll check this out every little bit. I'm going to cover these back up so those don't react anymore. You can probably see my gloves reacting, the outside of my gloves right now. And I'm just going to get that cleaned up over here, get it off my fingers, and then we'll throw this away. Okay, it'll take about 5 or 10 minutes for it to migrate down. We'll take a look at that, but let's get your answers locked in.
Migrate down to where?
They're going to migrate down and meet somewhere in the center. All right. Okay. So while we're doing that, let's do some work, and I think this is in your packet. I could be lying to you, but there should be a problem here, an airbag problem. Is there an airbag problem? Yes. All right. Let's do the airbag problem, and this is a legit airbag reaction. Okay. Automobile airbags contain this substance. Now, you might look at this and say, oh, I can name this one. And I'll bet you can't. Because you might look at it and it might look as if this is sodium nitride, right? But this is not sodium nitride nor nitrate. This is a substance called sodium azide. The sodium azide. And that's because if you look very carefully, what is the formula of the anion on here? What is the formula? It is N3 what? What's the charge on it? Single minus, exactly. So the azide ion is N3 with a single negative charge. So it is a polyatomic ion, not one that we've looked at before, combining with the sodium ion, which is Na, with a single positive charge. So this is a sodium azide. What happens, this is like a contact explosive type of thing. There is, inside an airbag mechanism, when you have an impact, there's some sort of cylinder that slides back and forth, and when the impact is large enough, it breaks through the cylinder, it collides with the sodium azide. Once it collides with it, there's a small explosion that occurs, and that small explosion occurs generating sodium metal and nitrogen gas. And it's the nitrogen gas that winds up inflating the airbag. So this reads, if an automobile airbag has a volume of 11.8 liters, we'd like to know what mass of sodium azide in grams is required to fully inflate the airbag upon impact. And we'll assume STP conditions. So somewhere at the end here, we want to calculate grams of the sodium azide that is required. So we're going to start with what we know. We know the volume is 11.8 liters. We know that the initial conditions are STP. What does STP stand for again? Standard temperature and pressure. So at standard temperature, we would have a temperature of how much?
0 degrees.
0 degrees Celsius, which is also how many kelvins? 273.15 kelvins. Okay. Now you could probably round off the 273 and we're fine, but I prefer to be a little bit more precise and take the 273.15. Just remembering that really it's only good out to these three significant figures. And standard pressure is how much?
1x.
1 atmosphere of pressure. Exactly. So now with this information, if we look at the ideal gas law, PV is equal to nRT. We know the pressure, we know the volume, we know the value of the gas constant R, we know the value of the temperature. The only thing we don't know is the number of moles. So we should be able to rearrange this equation and solve for the number of moles. Of course, when we rearrange and solve for the number of moles, we're solving for the number of moles of which stuff? Oh, be careful here. Which gas is going to be found in the airbag? Nitrogen gas, exactly. So when we calculate the number of moles, we're not calculating the number of moles of sodium azide, we're calculating the number of moles of nitrogen gas that are used to inflate the airbag. This is the only gas that's in here. So we'll find N by rearranging this equation. And we rearrange it by dividing each side by RT. RT winds up canceling out. And it tells us that the number of moles is equal to PV over RT. So we substitute in the values. Our pressure is 1 atmosphere, and of course that's really 1.00, etc. on up into infinity. Atmospheres. The volume is 11.8 liters. We're dividing this by R, the gas constant, which is 0.08206 liter atmospheres per mole dot K, and dividing it by the temperature, which we said was 273.15 kelvins. Once we go through all of this, we cancel out our units. Kelvins are gone, liters are gone, atmospheres are gone. We are now left with units of moles in the denominator of the denominator. If we have moles that are in the denominator of the denominator, where does that put them?
At the top.
Back in the numerator, exactly. So if they're in the denominator of the denominator, we flip that back up. They show up in the numerator because, again, dividing by a number is the same as multiplying by its reciprocal. Okay? So we'll go ahead and divide this out here, and we'll take 1, multiply it by 11.8. We'll divide it by the gas constant, and we divide it again by 273.15. Upon doing so, out to, I'm going to carry with an extra digit, so this is going to be 0.5264. Again, it should really only have 3 sig figs, but the label on this is moles. And again, this is moles of which stuff? Alright, so this is moles of nitrogen. So I'm going to go ahead and slide this over here just a bit. We're not looking for moles of nitrogen, we're looking over here for grams of the sodium azide. So with our moles of N2, our next step is going to be to do what? Convert moles of N2 over to moles of the sodium azide. Remember, if we have to go from one substance to another, which conversion do we use? Molar ratio. So on the bottom, we're going to put in moles of N2. On the top, we'd put in moles of the sodium azide. Which numbers are we going to put in here? On the bottom, we'd put in 3 moles. On the top, we'd put in how many? 2. All right. Again, those come from the coefficients here in the balanced chemical equation. Moles of N2 cancel out. Then, to calculate grams of the sodium azide, on the bottom we'd put in 1 mole of the sodium azide. On the top we'd put in grams of the sodium azide. So we go back to our periodic tables. We have 1 sodium. We have 3 nitrogens. 42.03 plus 22.99. We wind up with 65.02. 65.02. Put in the 65.02. Our moles of the sodium azide cancel out. We then take the 0.5264, multiply it by 2, divide it by 3, multiply again by 65.02. And once we do that, we wind up with an answer 22.817, etc. How many significant figures should be in the answer? And out to 3, we'd round it off to 22.8 grams. The label here would be grams of the sodium azide. Any questions on this one here? Okay, let's take a look, see if we have a ring yet showing up in this. I thought I was seeing one. Can you see one? Yeah, I can. Can you see this yet?
Yeah.
It's right there. It's a very, very super band. That's one of the really cool things about this. It comes in the forms of very super thin. I don't know, can you see it from there?
Not really.
And I don't know if I can move it. I'm going to try to not tilt this here.
You can see it.
Yeah, just barely. It's right here. It's going to get darker. It's going to, right now it's just a super fine ring. It's going to get fatter and fatter as it sits here. Maybe you can see it now. No? Probably just the ones that are closest here can see it. Okay, we'll set it down, leave it there. But as we look at this one, if it's at this point, see, I can't even see it when I lay it down. Here it is. Right here. Which side is it closer to?
The middle.
I don't think so. You got bad eyes then.
It's closer to HCl.
Yeah, closer to the HCl side. All right, closer to the HCl side. Let's see what we came up with. Closer to the HCl. And why would we say it's closer to the HCl? The majority of us were right. Why should we be able to predict this? The majority of you did predict correctly.
Higher density.
Well, what has a higher density?
HCl.
Okay. Higher density would be the same as saying higher molar mass. If it has a higher molar mass, what do we think that might mean about it?
It doesn't flow as easily.
Okay. It moves a little bit slower. Now, one of the things we haven't looked at yet in here, and this is where we're going to kind of be wrapping things up here today, turns out that, and by wrapping up, I know we still have like 45 minutes left here, 40 minutes. But when we talk about these, one thing we haven't mentioned yet about it is that the kinetic energies of all the molecules, all the particles that are in the atmosphere are identical on the average. Okay, so it doesn't matter whether we're dealing with light molecules or we're dealing with heavy molecules. All of the molecules, if they're at the same temperature, have the same kinetic energy. Now, Kinetic energy is a topic you would ordinarily cover in physics. And so when we look at this, let's talk about kinetic energy. And let's see, where do I have these? We'll pop down, we'll make a new one here. Talk about kinetic energy. I'm going to label kinetic energy as Ke. Again, this represents kinetic energy. And the formula for finding kinetic energy is equal to 1/2.
Mass times the volume squared.
Right. This is V squared. And what does V stand for?
Oh, velocity.
Yeah, and this is one of those things, if you've had physics before, you actually learn that V isn't velocity, it is speed. V is speed. Now, if you had physics before, if you're talking about velocity, how does velocity differ from speed? What's that? Velocity has a direction, exactly. So when we talk about speed, speed is just magnitude or the size of the value. We talk about velocity. Velocity has both magnitude and direction. So use vectors. If you take physics, use vectors to describe velocity. So V here stands for speed. M is the mass. V is the speed. And again, speed is not the same as velocity because velocity also has direction associated with it. So it turns out that the kinetic energy of all of the gases, as long as we have the same temperature, we say that these are equal, assuming that we are at the same temperature. Let's see if we can see the band yet. Oh, there we go. A little bit darker. Okay. You see the band there yet? You got it? Got it back there yet? You see it? Right here. Okay. So again, a little bit closer to the HCl. So now, we might have predicted it like this. So we could say that the kinetic energy of gas 1 is equal to the kinetic energy of gas 2. And that's true on the average. And this is, again, we'd say on the average. Because some molecules move faster, some molecules move slower, but if we're talking about the average speed of the particles, then their kinetic energies are equal. So what we could do is we could find out what that ratio is of masses and relate it to the ratios of velocities. We could then substitute in 1/2 mv squared is equal to 1/2 mv squared. We can put in subscripts of 1 here to designate gas 1, subscripts of 2 to designate gas number 2. Now if we're doing this mathematically, we want to simplify this a little bit. We could take each side here and multiply it by a factor of 2. If we multiply each side by a factor of 2, that gets rid of the factor of 1/2 on each side. Let's lump all the masses together on the left-hand side. Let's lump all the speeds together on the right-hand side. So again, let's move the masses to the left. Let's rearrange it so all the masses are on the left, and so all these speeds are on the right. If we want to do it so all the masses are on the left, that means we have to multiply each side by, oh, not multiply, but divide each side by m2. What we do to one side, we must also do to the other side. And so if we divide each side by m2, it's gone here on the right-hand side. If we then want to get all the speeds on the right-hand side, we are then going to divide each side by v1 squared. v1 squared. And that's going to get rid of them on this side right here. What we wind up in doing so is something that looks like this. It says m1 over m2 is equal to v2 squared over v1 squared. And very often, if we want to give these in terms of the speed let's say if we want to give these terms of the ratios of the speeds, we would then take the square root of each side. And again, I'm taking the square root because what we really want to do is we want to talk about the speed at which they reached a particular point here. That means we're going to take the square root of each side. We take the square root of each side, we wind up saying that the square root of m1 over m2 is equal to v2 over v1. Now you might say, well, what the heck does all this mean? Well, what this means is this, is that if we were to look at the ratios, basically the larger the mass, that is, if m2 is greater than m1, and if m2 is greater than m1, the value of this side is going to be less than 1. So in other words, v2 over v1 is going to be less than 1. In other words, v2 is going to move at a slower speed than v1. So if we talk about that then, if we say that our v1 is designated as, well, let's see, over here, we'll look at your left and right. If this is your 1, which is your NH3, your NH3 is the one with the lower mass. Over here, your HCl is the one with the larger mass. So a lower mass over larger mass is going to tell us that it's equal to a higher speed over a lower speed. So again, we would expect that the NH3 is going to be the one that winds up traveling faster on down the length of the tube. And so when we look at this as a law, this is a law of diffusion. When we talk about diffusion, diffusion is how things spread out from a point source. Okay, if we're talking about the diffusion of gases, if somebody farts, for example, okay, it's going to spread out from a single source in here, and that would be an example of diffusion. Okay, and what we could say is that the speed is, now we want some label in here. Is this going to be a direct proportion or an inverse proportion if we look at this equation? We look at this. Is this representing inverse or direct? Inverse. This is an inverse. It's not simply an inverse proportion. We would say it's inversely proportional to the square root of the mass. And that's exactly what we're showing here. We're showing that this is the square root of the mass. So we say it's inversely proportional to the square root of the mass. And this is the law of diffusion. So basically, heavier molecules will diffuse slower. Lighter molecules are going to diffuse faster. Now, this relates to another concept in your textbook called effusion. And effusion is different than diffusion. Effusion is defined by something called Graham's law of effusion. And Graham's law of effusion is, first of all, we have to define what effusion is. Effusion is how particles move through a small opening or pore. If, for example, I were to take this gas valve on here and open it up, said only just a few molecules could escape at a time. What would happen is that turns out that the smaller, faster moving molecules find their way to the hole or the pore first. And that's why if you have a balloon filled with helium, what happens to a balloon filled with helium over time? It winds up shrinking. It winds up shrinking because what's happening, the molecules of helium, or actually atoms of helium, are smaller than the molecules of air, and they wind up diffusing faster, moving out of the balloon, than molecules of air wind up moving into the balloon. As a result, then the balloon winds up shrinking. Now, unfortunately, we have someone with latex allergies here on campus this year, and I can't bring this out and show it. It used to be one of our lab projects. Have you talked about lab projects yet, or is that coming up? Must be coming up in lab. Okay. One of the lab projects we used to do is we'd have the option for students to fill up different balloons with different gases. And in one balloon, you'd have helium, another one you might have air, another one carbon dioxide, and then we might have sulfur hexafluoride and another one out here. Well, it turns out that when you fill up a balloon with sulfur hexafluoride and seal it, it doesn't shrink over time. What do you think it does? It actually expands, and expands to the point where it actually winds up bursting. And that's because molecules of sulfur hexafluoride are larger than molecules of air. As a result then, molecules of air go faster into the pores of the balloon than molecules of sulfur hexafluoride can escape from the balloon. And as a result then, the balloons actually winds up getting larger, which is just the opposite of what helium does, and they wind up shrinking up. And it's a really cool thing to wind up observing. But it deals with Graham's law of effusion. And Graham's law of effusion is very similar to the diffusion law, and it says something like this, that the rate of effusion for gas 2 over the rate of effusion of gas 1 is equal to the square root of the molar mass of gas 1 over the molar mass of gas 2. And we could go back then and make the same type of statement that we did here for diffusion, and that is the rate of effusion is inversely proportional to the square root of the molar mass. So with this in mind, here's what I'd like for you to do. Let's compare the rate of effusion of helium and xenon. Let's compare the rate of effusion of helium and xenon. And this here is your next question on the Socrative app. Use your relationship to figure out which one effuses faster, and then tell how many times faster it effuses. Before you lock your answers in, I'd recommend that you compare with at least another neighbor or two to see if you're thinking the same thing. Give me another minute or two. Let's take 30 more seconds. Okay, let's lock in our answers. Counting down, 5, 4, 3, 2, 1. Correct answer is helium would effuse at a rate that is 5.757 times the rate of helium. So it looks like we came up just about everybody with the correct number, but why does helium effuse faster?
Because it has a smaller molar mass.
Smaller molar mass, just like we observed right here. The one with the smaller molar mass is the one that is going to travel faster. Now, if you're going to show this correct in an equation, I would ask yourself that question first, because I always, personally, when I do work, I hate numbers less than 1. If possible, I like to deal with numbers larger than 1. So if I'm going to look at my two rates, rate 1 over rate 2, I want to put the bigger one on top. So again, which one would I think is going to travel faster? Or which one should you think is going to travel faster? You should think it's helium. So I would show it like this. I would say the rate of helium or the rate of xenon. And of course, again, if we look at our equation, remember, here's a subscript of 1, here's a subscript of 1 here. We flip-flop those places. So this is going to be the molar mass of xenon over the molar mass of helium. Once we put them in like this, we then substitute in those molar masses, which for xenon is 131.29. The molar mass for helium is 4.008. We then take the square root of it. We take the square root of it. We do get that answer we saw you come up with, which is 5.727. And of course, that is the rate of helium to the rate of the xenon. Remember that they have an inverse proportion. The lighter they are, the faster they wind up traveling. And so helium travels, or has a rate of effusion of 5.727 times that of the xenon. Now, when you do your homework, you may not always be doing it in terms of rate. You might be asked for effusion or diffusion time. How is rate related to time? Mathematically, how are rate and time related to each other?
Rate is the amount of time it takes.
Rate is not the amount of time it takes. It's an inverse proportion, exactly. If you were traveling from here to Duluth, if you traveled at twice the rate, it would take half the time. So if we then wanted to express this relationship in terms of time rather than rate, if I want to put time of one over time of the other, which subscript would I give for the time that's on the top? And which subscript would I give for the one that's on the bottom? Would I put time of helium or time of xenon on top? Time of xenon, exactly. And then we'd put the time of the helium on the bottom. And that again is because rate and time have an inverse proportion to each other. If something travels at a greater rate, it is going to take less time. And so that's why these two, if we have a numerator here, it must be in the denominator over here. And so again, this is this whole thinking that we started with on day 1 in here when we talked about the gas laws. Many of these things with gas laws and such And that's just starting with gas laws. When we get into our next chapter, we're going to be talking about energy production. Okay, we're going to be looking at thermal chemistry, and we're going to be talking about things that are inverse proportions and direct proportions. So we need to conceptually think about these things, what the implications are, and how we write them into our equations. Okay, any questions on these? All right. Now, to look at this, what we have been looking at is something called the kinetic molecular. We haven't really used this word yet, but we've been looking at the kinetic molecular theory of ideal gases. And we refer to it as an ideal gas law. Now, some of the assumptions we make when we look at the ideal gas law and talk about an ideal gas law is that there are some assumptions. And one of the assumptions we've made at this point is that the size of the particles are negligible. We made the assumption we can ignore the size of the particles. In other words, if we have a gas, the assumption we made is we could compress it down to like 0 volume. Okay? And that's what an ideal gas would do. Another assumption that we've made is that the average, and we talked about this here earlier today, is that the average kinetic energy is directly proportional to the absolute temperature. In other words, it's temperature in kelvins. And so that's another assumption that we've made. And a third assumption we make is that the collisions of particles are completely elastic. So for an ideal gas, these are the assumptions that we've made, and these are the assumptions that go into the ideal gas law. Now again, what it means that if we're talking about the size of the particles are negligible, that means if we had a gas, we could compress it down, we could pretty much compress it down to 0 volume, because it's as if the particles themselves don't have any volume. This one here speaks for itself. We talked about that before. But then collisions of particles are completely elastic. If you've had some physics before, you'll talk about elastic collisions and inelastic collisions. What is an elastic collision? Things come together, and what happens to them? They wind up bouncing apart from each other. There's no loss of any energy anywhere in there. They come together, they bounce off, and they go like that. If it's an inelastic collision, then that means that the particles collide together and they stick together. They don't wind up coming apart, but in completely inelastic collision, they stick together. The reality is most collisions are somewhere between completely elastic and completely inelastic. The assumption we make in kinetic molecular theory is that they're completely elastic. Now the reality is that there is no such thing as an ideal gas. So even though we spend time talking about ideal gas laws, we have our ideal gas law formula, and we're going to continue using those throughout the semester, there is no such thing as an ideal gas. What we have is real gases. So again, there's no such thing as an ideal gas. We only have real gases. And so if we were to look at some of the implications of what real gases are, we could look at the molar volume at conditions of STP. In other words, the molar volume, remember, is for 1 mole of a gas. And if we looked at the value of the molar volume at STP, we find out that they're all pretty close here to 22.4. Remember the size of the box I brought in here the other day? They're all very close to 22.4 liters. The 22.4 liters, I think it says 22.42, is the actual molar volume. Okay? But now, notice what happens to the size of the molar volume the larger the particles become. The larger the particles become, the size of the molar volume becomes a little bit smaller. Okay? In an ideal gas, okay, I lied. ideal gas, that volume there sits at 24.41. Okay. Now, it turns out that if we want to take into account real gases, we can't ignore particle size. We said that when we look at an ideal gas, we are pretty much saying that we can ignore particle size. The reality is we can't ignore particle size. And if we were to look, and these are figures now in your text, this is the last section, 6.10 in chapter 6. If we were to look at a gas like argon and subject it now, the scale here, if you look at these are very high pressures. We're talking pressures of 200, 400, 600, 800, 1,000 atmospheres. These are very large pressures. And at that point, if you're compressing something, eventually you're going to get down to the point, because the particles actually take up space themselves, that they can't be ignored much. We see here at pressures below, say, maybe about 100 atmospheres, that if we look at that molar volume, that the comparison is very much the same. But as we go further away and get much, much larger pressures, we see that if we look at a real gas like argon compared to an ideal gas, that there becomes to be a departure between how a real gas behaves and how an ideal gas behaves. And again, that comes from the fact that when we compress a gas, pretty soon then, these spaces between them become closer and closer to the size of the particles themselves. And again, we can't ignore that. A second factor that we've ignored is that turns out that we have intermolecular forces. And they play some effect, making it so that the collisions are not completely elastic. If molecules have an intermolecular attraction, that is, if they attract each other, they're going to come together and they're going to want to attract each other before they wind up bouncing apart. Okay, just like if we had a big collection of magnets, and if we threw them out, a lot of them will wind up coming apart, but if they are going to hit each other with some force, they're going to want to track each other for a small period of time before they fly apart if they've hit each other fast enough. And so there is going to be some inelasticity involved with that. So if we looked at something like xenon again, and this one here is showing what happens with the temperature, at higher temperatures, pretty much we can ignore that, but once we get down, this is now a temperature scale in kelvins. Once we get down to lower temperatures, the departure from an ideal gas and a real gas winds up becoming larger and larger. And that's because as we lower the temperature, what happens to the speed of the molecules? They slow down. If they slow down or are moving slower, what are the chances that they're going to interact with each other? There's going to be a lot greater chance that they're going to interact. So if they're moving slower, those intermolecular forces now have a greater chance to act with each other. If they have a greater chance to act with each other, then there's going to be a greater departure from this ideal behavior. And as it says here, and you want to know, what should we know from this? Well, here's what you should know from this, is that intermolecular forces are important the lower the temperature becomes, and the spaces between particles become significant at higher pressures. Those are the things you should know about real gases. So particle size, again, is important at high pressure. Intermolecular forces are something that is important at low temperature. Again, at high pressure, they are significant because once you start compressing them, these spaces between them become a lot smaller. And be just like the people in this room. I mean, you feel like right now you've got a lot of elbow room and everything. You can stretch out and whatever else. But you start taking the size of this room and squishing it down, what happens? Well, pretty soon you don't have any room to spread out. Okay? So the same thing is going to be true then at high pressure. As we compress them together, you no longer have that elbow room. And again, with low temperature, it becomes important because molecules are slowing down. Just like in here, if we were to slow down, you have more chance to interact with each other than if we were running around in here very rapidly. Now, how is this all taken into account? Well, this right here is what we call the van der Waals equation. And the van der Waals equation has a couple correction factors in there. There's a correction factor in here for intermolecular forces, and there's a correction factor here for the particle volume. Now, the way that these are determined is like this. It's very similar to what you do when you have been doing your labs. You've been doing, in a number of your lab activities thus far, you've been doing some curve fitting, okay? And in your curve fitting, you are doing things like finding slopes of lines and everything. And so basically, if you look at these graphs, you notice that these graphs take on the shape of a parabola. Okay, you can't, it's a little hard to tell here because the slope is so wide on these here, but you can see that these here wind up taking on these shapes of the parabolas. And so then what's done then is that a real gas is taken, we observe their behavior over a variety of pressure conditions and temperature conditions, and then through curve fitting, we come up with these variables, which are A and B, not variables, these are constants, which wind up getting plugged into this equation right here. And if we look at this van der Waals equation, notice it still takes on the form very similar to the ideal gas law. The form is PV is equal to nRT. But again, you have a small correction in the pressure that takes into account the intermolecular forces. We have a small correction for the volume, which is taken into account here with that particle volume. Now, just like with the vapor pressures, there's no need to memorize these values here. These are one that each different substance has its own van der Waals constant for those common gases. And again, it'd be determined very much like you're doing in the lab by going through a bunch of curve fitting techniques to find out which values of A and B give the best fit for your real data. So calculations on exams, you will not do any calculations on your exams with the van der Waals. You might in one of your homework, or one or two of your homework problems. On the exams we won't. I expect you to know Pivner. I do expect you to be able to explain how or why real gases differ from ideal gases. That would be an exam type question I'd like for you to know. So, any questions? All right, we have about 8 minutes left. I brought with some liquid nitrogen today to play with if you want to see us play with that. Anybody, I mean, you're free to leave if you want, but if you want, I'll play with some liquid nitrogen for a while. And you can come over here and play with it if you want. I'm going to take this out here, and I'm actually going to pull the liquid nitrogen from the back. And I like to put the liquid nitrogen in here so you can see what I'm doing with the liquid nitrogen. And I'm not going to have time to fully play with this here today, but we'll throw in so we'll have to do as much as we can as quickly as possible here.
It's starting to remind me of the Minnesota summer.
There we go. There we go.
But you're getting this table all over.
There we go.
Look at
With that a little bit. Okay, now, of course, one of the things we can do with this, here's one that I like to do with it. I like to take the piece of rubber hose, and actually I'm going to put this screen up right here just in case we have some sort of issue with this. And I have a piece of rubber hose that I took out here, which you can see is nice and stretchy. And I'm going to drop this into the liquid nitrogen. Now, notice what's happening here. Any idea why this happens? You can hear what's happening and see what's happening inside here when I have this lowered in. Okay, what's happening is that this rubber hose is warmed and placed into liquid nitrogen, which of course is really cold. That causes the liquid nitrogen to boil. When it boils, it converts from a liquid into a gas, and it winds up shooting out the end of the hose. Okay, so it shoots out all of the liquid. And now that the hose has reached the same temperature as the liquid nitrogen, notice now it's no longer shooting out the end. But what I can do with this is I can come over here and see how this winds up becoming very brittle. Okay? Yeah. Now, thing is, you don't want to pick that up quite yet. Okay? You can let that cool down a bit. I do annoy the maintenance staff a little bit. When I do that, you can pick it up. You don't want to get frostbite on yourself there. So that's one thing we can do with it. I think when we looked at this the other day, we did not put any of this in water. So I can go ahead and pour some of this into some water here, which we'll do. And if I were to come over here now and take my laser pointer.
That's a cool Halloween trick.
Notice what happens. Laser pointer, as you look in this, what we're observing is what's called the Tyndall effect. And if you ever wonder, if you've ever been to like a concert, rock concert, whatever, and look at their laser show, you might see the path of the lights. You can see them going all the way down to the floor or whatever throughout the stadium. One of the reasons why they use fog machines in there is because what they're trying to do is utilize the Tyndall effect to wind up spreading that light out at the different angles. So that's the whole purpose behind the fog and the smoke at those shows when you do the light show, because then you can see the beams of light and whatever coming down when we show those. Another thing I can do here is I can drop in a banana into there, and while we're waiting for this, I can take my nitrogen, pour it into the Pringles can. All right, there we go. Now, of course, why is this happening? Yeah, started. All right, of course, we got that. We come back to here, notice what's happening with the liquid nitrogen. Where does that liquid nitrogen sit on this?
On the top.
On the top, which indicates it is less dense than water. And the whole banana trick, what is this about? Well, the banana trick is because I think I've told you I've been working on some house repairs lately. And turns out there was one day that I forgot my hammer. And so, fortunately, because I'm a chemist, I had a supply of liquid nitrogen sitting around. I took my lunch out, popped the can out of my lunch, threw it into the liquid nitrogen, and I had myself a hammer. Alright? So, that's like in a few minutes what I wish I had more, because this is such fun stuff to play with. But one of the things I'd like to do here before you leave is I'd like to pour this into here. And before you leave, perhaps you may want to cool yourself down a bit, because like I get a little hot up here. You can come here and put your hands into some liquid nitrogen if you want before you leave. Just don't leave it in there, because of course if you do, it's going to be the same thing like the rubber hose. All right? We don't want that. But if you want to check this out, you form a small vapor barrier around your hand. You can check this out and see how this works. That's it.